Greetings to the respected faculty. Today, I will be presenting on the topic homogeneous differential equations as a part of the course Differential Equations and Vector Calculus. My name is Lasya Mandapati and I am from CSE AI and ML B section. My roll number is 24951A6686. Differential equations are fundamental in engineering, physics, and artificial intelligence as they help in modeling dynamic systems. Homogeneous differential equations form an important class that allows for specific solution techniques. In this presentation, we will explore their properties, solving methods, and applications. Let's begin. Before diving into homogeneous equations, let's briefly discuss differential equations in general. Differential equations describe relationships that involve derivatives. Derivatives simply represent rates of change. They are widely used in various fields such as engineering, physics, and economics. We classify differential equations into two types: ordinary differential equations and partial differential equations. Ordinary differential equations, or simply ODEs, involve functions of a single independent variable and their derivatives. Partial differential equations, or PDEs, on the other hand, involve functions of multiple independent variables and their partial derivatives. Homogeneous differential equations are a type of ordinary differential equation that exhibit special properties, making them easier to solve systematically. Now, let us define homogeneous differential equations. A first order differential equation is written as m of x comma y dx plus n of x comma y dy is equal to 0, where m of x comma y, or simply m, and n of x comma y, or simply n, are functions of x and y. A differential equation is homogeneous if m and n are homogeneous functions of the same degree. This means they satisfy the function f of dx comma dy is equal to t to the power of n f of x comma y for some integer n. By rewriting this equation in the form of dy by dx is equal to f of y by x, we can simplify the equation using the substitution method that we will discuss next. Differential equations are classified into two forms: exact and non-exact. An equation mdx plus ndy is equal to 0 is said to be exact if the following condition holds true. That is, dou m by dou I is equal to dou n by dou x. That is, if the partial differentiation of m with respect to y is equal to the partial differentiation of n with respect to x. This condition is satisfied, a potential function f of x comma y exists, where df is equal to mdx plus ndy. For non-exact equations, this condition does not hold true, meaning we cannot directly find f of x comma y. In such cases, we use a function called an integrating factor, or simply IF, to convert it into an exact equation, which we will discuss next. For a non-exact equation of the form mdx plus ndy, we introduce an integrating factor. Like I've said before, it is represented using the symbol IF. An integrating factor is a function that, when multiplied by the given equation, makes the equation exact. A commonly used integrating factor for solving homogeneous differential equations is 1 by mx plus ny. Multiplying the equation by this factor ensures that the equation becomes exact, allowing us to uh, solve the equation using the methods for exact equations. Finding a suitable integrating factor is key to solving many differential equations. Now, let us solve an example to illustrate these concepts. For the example problem, let's solve the homogeneous differential equation x square plus y square dx minus 2xy dy is equal to 0. As you can see, this equation is homogeneous as all the terms in the equation are of the order 2. We can also see that the equation is in the form of mdx plus ndy is equal to 0. And so we can identify that m of x comma y, or simply m, is equal to x square plus y square. And n of x comma y, or again simply n, is equal to minus 2xy. To check if the equation is exact, we must first compute the partial derivatives. That is dou m by dou I and dou n by dou x. Now let us first start by finding dou m by dou n. Hence, we partially differentiate x square plus y square with respect to y, through which we get dou m by dou I is equal to 2y. And now we partially differentiate minus 2xy with respect to x. On doing so, we get minus 2y. Hence, 2y, we can see that 2y is not equal to minus 2y. And hence, dou m by dou I is not equal to dou n by dou x. Hence, the equation is not exact. Therefore, we need to find the integrating factor if is equal to 1 by mx plus ny. Now, let us go through the solutions step by step. First, let us start by computing mx plus ny. On doing so, we get x square plus y square minus 2xy. Here, we can see that mx plus ny is not equal to 0. Hence, if, or the integrating factor, exists. Now, we can finally say that the integrating factor if is equal to 1 by x square plus y square minus 2xy. After applying the integrating factor and solving, we obtain a general solution f of x comma y is equal to c, where f of xy is derived from integrating m and n. So we can see that after multiplying the integrating factor with the non-exact equation x square plus y square minus 2xy, we obtain a function, an exact equation. And on integrating this, where to solve this equation, we integrated the solution of the equation is integral of m plus integral of n is equal to c, where integral of m is taken in such a way that y terms are taken as constant, and in integral of n, no x terms or any terms consisting of x are not taken into consideration. Hence, we can say that the equation f of x comma y equal to c represents the implicit solution to a differential equation. Using these methods, we can systematically solve any homogeneous differential equation by first checking if it's exact, and if it is not, finding an integrating factor if necessary, and lastly converting it to an exact equation, and solving for f of x comma y equal to c. Now let us discuss applications of homogeneous equations. Homogeneous differential equations have many practical applications. For example, they are used in electrical circuits and are used to model voltage and current flow. Similarly, they are used in thermodynamics to describe heat transfer and temperature variation. They are used in fluid dynamics to help analyze fluid flow rates and pressure distribution. In economics, they are used in market equilibrium and financial modeling. In physics, they are applied to motion, force, and wave equations. Hence, we can see that understanding these equations is crucial for engineers and scientists in multiple domains. To summarize, we can say that we covered the classification of differential equations. That is, the classification into ordinary differential equations and partial differential equations, the general form of homogeneous differential equations, the difference between exact and non-exact equations, the use of integrating factors to solve non-exact equations, a step-by-step example problem and solution, real-world applications in engineering and physics. Lastly, mastering these concepts will help us in solving many practical problems in science and technology. That concludes my presentation on homogeneous differential equations. Thank you for your time and attention.